This is a somewhat extended version of the talk we gave at Informs just a couple of weeks ago about GPU acceleration of Express 9.8. My name is Imre Polik, and I'm the manager in charge of developing the linear and continuous optimization solvers, and in particular, the GPU accelerated version of the hybrid gradient algorithm. So first, couple of words about what Express is and where it sits with the FICO software stack, in case somebody is not familiar with it. We have a comprehensive business analytics suite built from several components. What we are going to be interested today is the Express solver, but it also has a very extensive modeling layer with APIs to any language that you wish. And we also have some visual API and user interface and database management tool called Insight. These are all managed from Express Workbench to facilitate development. And we also have a few custom-made solutions built on top of these components. But what we are going to be talking today is the optimizer component, the Express solver, and especially the linear optimization solvers within that. We have a number of algorithms to deal with the linear optimization problems. We have primal dual simplex, we have network simplex, we have barrier or so-called interrupt methods. And then as of a few years ago, we also have a hybrid gradient algorithm implemented for linear optimization. So this is very different from the other algorithms in that it's a first-order method for solving linear optimization problems. So in optimization terms, we are trying to find the saddle point of this problem, which is just coming from the optimality conditions for linear optimization. The iterations or the updates to the primal and dual solutions are fairly straightforward. On the primal side, we update the primal iterate with the current dual error with some weight, and then we take the positive part of that because x is a non-negative variable. On the dual side, the dual update is similar. We are taking the current primal error and then multiply that by a weight and subtract that. The only trick is that we use both the current and the previous primal iterate when calculating the parameters. So this is like a weighted average of the last two iterates or last two errors. And the beauty of this algorithm is really that it has no factorization. It has two matrix vector multiplications per iteration. Once we need to multiply by A, and once we need to multiply by A transpose. The rest is very quick operations, matrix, vector products, vector updates, norms. So those must be pretty quick. So it has very, very little memory overhead. For any algorithm, we already have both A and the row representation of A, so technically A transpose in memory. So the only extra memory is really used for the bookkeeping of the algorithm. On the other hand, this algorithm is only linearly convergent. It's a first-order method, which means that it can find solutions to a reduced tolerance to like 10 to minus 2, but it could be very slow to reach our standard 10 to minus 6 feasibility tolerance, which is fairly standard across all solvers and all algorithms. So hybrid gradient is struggling with that, but it can find relaxed solutions for problems fairly quickly. This has been available since Express 9.4, like a couple of years ago. And it has received significant improvements both to stability and performance. It's a fairly new algorithm in the literature, and there are a lot of tips and tricks and special methods to try to speed up this linear convergence or try to circumvent cases when the algorithm is not converging. And a bunch of these tricks were implemented in Express 9.6 and also in 9.8, which is the current release. So as you can imagine, with the method that's somewhat challenging to converge. There's a whole bunch of convergence criteria. So these are the three things we are checking. We are checking the primal error, we are checking the dual infeasibility, and we are also checking the complementarity, the gap or duality gap, the difference between the primal and dual objective values. And we have tolerances for all three of these. And we also have them in the absolute and in the relative sense. And so as you can see, the defaults here are only 10 to minus 2, which is much more relaxed than the 10 to minus 6 default for like a barrier or simplex algorithm. That is because the hybrid gradient is often simply just cannot go that far. So a simple algorithm like this actually has a very attractive property in that it is much less sensitive to numerical inaccuracies. And so there's no factorizations, no solves in the method. And there's no matrix that's becoming ill-conditioned or nearly singular as the algorithm is converging as it is for the barrier method, which actually means that single precision, like float implementation of the algorithm works almost as well as a double precision version. It's important to say that only the actual hybrid gradient algorithm is in single precision. The pre-solve and post-solve that we are adding still uses the standard double precision. Quite surprisingly, if you could say, the convergence rate is not affected, and the number of iterations stays roughly the same between single and double precision. There's a bit of memory overhead, surprisingly, because now we have to store the matrix both in double precision and also in single precision. But in exchange, we do get some speed up because operations on the single precision matrix are somewhat faster. Not terribly faster, only 10-15%. And this is coming more from the better memory throughput than from faster CPU operations. It's very important that the two versions of the algorithm are compiled from the same source file to guarantee that the two algorithms are equivalent, and so we don't have to worry about the two versions diverging over time. And if the numbers in the matrix are quite nice, we have actually observed a few cases when the single precision and the double precision solution paths are actually the same, which we were quite surprised about. That being said, we defaulted the algorithm to double precision on CPU simply because that's also the default for the rest of the algorithms, and the speed gain is only about 10-15%. So it's not a game-changing advantage to run it in single precision. So how did we implement this hybrid gradient algorithm on a multi-threaded CPU? Well, as I said, there's two main operations. There are two matrix vector products in each iteration, and these parallelize fairly well on the CPU. Of course, if the matrices are dense, it works much better. We can just use like off-the-shelf dense blast routines. But sparse matrix vector multiplications can also parallelize fairly well. On the other hand, if you use too many threads, that can actually hurt performance. There simply isn't enough work per thread, and the memory or cache overhead actually eats up all the speed up coming from multi-threading. On the other hand, vector operations, or like what's called BLAS1 in linear algebra, don't typically get much speed up from CPU threading. Simply, there's not enough work done per data. Here, for like if you calculate the 2 norm of a vector, each element of the vector is seen only once. Take the square, and you never look at that piece of data again, but you still had to fetch it from memory through cache, and then you have to replenish your cache every time you move on to a new chunk of data. So a lot of implementations don't even parallelize BLAS1 routines, and there's as I said, there's not much speed up from that. In our implementation, only the blast 2 calls are parallelized, so only the matrix vector multiplications in each iteration. And we don't use off-the-shelf routines. We implemented our own linear algebra kernels to have some finer grained control over it. So for a while, the conventional wisdom about hybrid gradient method was that the bulk of the work is the matrix vector multiplications. So it is perfectly enough to parallelize just those. But as it turns out, most large and sparse problems are so sparse that the number of non-zeros per columns is only a handful. Like I have a table here with 5 well-known public instances, and the first few of them have like 2 to 4 non-zeros per column on average. So that means that calculating A times X for any vector X, be it sparse or dense, means that it's only about 2 to 4 times the cost of, say, calculating the norm of X or taking a scalar product with X. So it's not quite the quadratic amount of work that you would expect. It's closer to a linear amount of work. And we have a whole bunch of other similar linear operations. We have to take norms. We have to do updates on the primal and dual side. We have to calculate norms to check for convergence criteria. And so the actual time that is spent in matrix vector multiplications for most of these problems, the first four problems, is only about 20–30%. And even the more dense ZIP05 problem, which has 37 non-zeros per column on average, even for that problem, only about 70% of the time is spent in matrix vector multiplication. Why is that important? It is because if we just speed up this part, just the matrix vector multiplication, by moving it to the GPU, and let's say you achieve a tremendous theoretical speed up for that part, meaning you can do that in 0 time, the matrix vector multiplication, then because there is a significant amount of work done outside of matrix vector multiplication, the best speed up you would get is actually very little. Even for the largest problem, which has 70% of the time spent in matrix vector multiplication, the theoretical best speed up would be about 3. So that means that unfortunately, the entire algorithm needs to be moved to the GPU, not just the matrix vector multiplication, but all the updates, feasibility checks, scalar products, norms, anything. And that's exactly what we did. We moved the entire algorithm to the GPU. So how does this work? There's a very little data transfer between the GPU and the CPU because that is actually a fairly expensive step. You don't want to communicate too much between the CPU and the GPU. The problem is transferred at the beginning, and then all the iterations are executed on the GPU, and then the results are read out at the very end. And during that time, all operations are parallelized, not just the matrix vector products, but all the norm scalar products, convergence checks, and everything. Here we use a combination of existing kubeless kernels and some of our custom NVIDIA kernels. And we have both single and double precision versions of the algorithm. They're compiled from the same source file just to make our life easier. A very important thing, which is fairly new in the GPU realm, is that all of our operations are deterministic. Which means if you run the same problem on the same GPU, then you will get the same solution and the same solution path. If you run it on a different GPU, then because it has a different number of CUDA cores, it might have a different solution path and a different result in the end. But mathematically, the algorithm is actually equivalent to the CPU version. Again, because the CPU is probably using a different number of threads than the GPU, it will have a different solution path, but mathematically the two algorithms are equivalent. And in practice, we've observed the same convergence behavior and the same number of iterations to convergence. So what kind of GPUs have we tested? Well, we really tried to cast a very wide net and try to cover everything. So the slowest one or the simplest one is the MX450, which is just a simple laptop GPU from 5 years ago, I believe. And then we have the RTX 4070 and the 5070. These are fairly high-end gaming GPUs. The only difference is that the 5070 has faster GPU memory. The blue ones are offerings you can get from AWS, and the T4s are older and simpler one. The H100, up to very recently, this used to be the highest end GPU, but now it's been dethroned. But it's still a very, very capable GPU. And for a CPU comparison, we just use the Graviton 3, which again, you can get from AWS, fairly standard. So one thing that is obvious looking at this table is, first of all, let's talk about memory. So the MX, also all GPU cards have some GPU memory on the card itself. If they run out of that, they can swap out and use some of the CPU memory, but that's going to be very costly and it will slow things down tremendously, but at least it will not fail without of memory. The MX450 has only 2 gigs. High-end gaming cards have 16 gigs. And that's actually where the low end, I would say, enterprise cards start at 16 gigs, and then they go up to 80 or 96 gigs of memory on the card. So that's a huge differentiator between, I would say, consumer grade and enterprise grade cards. The number of CUDA cores, there isn't such a big difference because the gaming cards already have over 8,000, and that's maybe you could have 50% more, but that's not a huge difference. On the other hand, the double precision floating point speed is another huge differentiator. The H100, one of the highest end cards, has double precision speed, only half of its single precision speed. So this is, the theoretical maximum. On the other hand, gaming cards or lower end cards have much worse double precision performance than single precision performance. In terms of bandwidth, there isn't such a huge difference between high-end gaming cards and enterprise-grade cards. So after this, it will be interesting to see what kind of speeds you can get. So here's a simple overview table of the 5 instances. These are the same 5 I discussed earlier. These are public LPs, fairly large. The smallest one has 1 million non-zeros. The largest one has 300 million non-zeros. And then we ran them with 3 CPU setups and 8 GPU setups. So first of all, there's not much difference between the CPU timings. They're still within 20, 30, maybe 50% of each other. And that's, any CPU can get these days, they'll roughly be the same performance. So for the comparisons for the rest of the talk, we will just use the Graviton 3, because this seems to be faster than the others. And just to highlight, on the CPU implementation, only the matrix vector multiplication was parallelized, and not all available threads were used because sometimes using too many threads on a CPU actually hurts performance. On the GPU side, one thing that we can see is that MX450, which has only 2 gigabytes of RAM, struggled with the 2 largest tip instances. They simply didn't fit in its 2 gigs of memory, and it would have been able to solve with enough CPU memory, but the time is way more than an hour. Also, for the The high-end cards, like the H100, does give a speed up even for the very largest problems, like the ZIP05, which has 300 million non-zeros. For the smaller, let's say smaller problems, which have only around 10 million non-zeros, the performance between the H100 and the rest of the cards is fairly similar. Again, there's just probably not enough work even for even with 10 million non-zeros, there's not enough work for feeding, say, 10,000 queued up cores at the same time. Also, if we try to parallelize the CPU work a little bit better, like spend some extra effort in parallelizing all the BLAS1 operations, maybe we could get a factor 2 speed up, but definitely not the kind of speed up that we have here, that even with the MX450, which is just a simple laptop GPU, you can have a 5 to 10 time speed up in singular precision compared to the Graviton, which is a fairly high-end CPU. And some of these speedups are actually very significant. I mean, you can get over 20 time speed up, or even better than that, like 50 speed up on the high-end cards. So let's look at some graphical representation of the same thing. So again, these are the same 5 instances. And then we now have both the single precision and the double precision speedups compared to the Graviton 3. The first lesson here is that even the gaming GPUs actually offer very good speed up, or even the simple AWS instances offer very good speed up in general. However, the high-end cards like the H100, they actually offer extremely good speed up even for double precision operations, which is not surprising, because if we go back a couple of slides, then we can see that the H100 has 25 teraflops of double precision throughput, which is way more than anything else in this table. And that's best represented by like the ZIP03, which seems to be getting the biggest speed up. It has a over 60 speed up as compared to the CPU operation. And the ratio between single and double precision is roughly 2 for the older cards, which is again not very surprising. Like the older cards are much better used for singular precision. They're simply not they don't have optimized double precision floating point modes. So another common question that we receive is, how does this compare to? So when should I use GPU? What does it depend on, whether the GPU versus the CPU will be better? And here we have a scatter plot of not just those 5 instances. This is over 100 instances, both public and our own clients. And we just plotted the GPU versus CPU speed up on the horizontal axis versus the number of non-zeros in the problem matrix on the horizontal axis. And there's a couple of good news in this picture. The one is that the trend line is definitely going upwards. So that means the larger the problem, the more speed up we can get from GPU, and that's exactly as expected. The other one is, if the problem is very small-ish, let's say, I don't know, the limit seems to be between 100,000 and a million non-zeros, but even for a million non-zeros, if you look at the overall picture, under a million, you're pretty much better off using the CPU implementation. But over a million non-zeros, the GPU implementation starts to win simply by raw power. However, there are some outliers here. And one reason for those is that the two algorithms are, of course, not exactly identical, and there are some numerical differences and there's some convergence differences, which actually affect the performance. So each iteration that we do on the GPU is much faster than the iteration we do on the CPU, but we are not getting the same convergence. But those kinds of outliers are fairly rare. So as I said before, we do support a whole bunch of GPUs going back to 2018. And the only thing we require is this compute capability 7.5, which was introduced in late 2018. And this implementation is now available as a beta in Express 9.8. We require NVIDIA driver version 580 and CUDA runtime 13.0. These are also in line with the compute capability 7.5 requirement. We support only a single GPU, so you cannot use two GPUs connected together. And the GPU memory requirement, you can actually calculate that upfront, both for single and double precision. The double precision requires about 50% more memory on the GPU than the single precision version. So for like an example, if you have 100 million rows, 100 million columns, and about billion coefficients, so that means you have about 10 non-zeros per column. So that will require 23 gigs of GPU RAM in single precision, about 38 gigabytes in double precision, which are well within the realm of high-end enterprise grade cards. Definitely not on the gaming setups. We support all platforms that are supported by NVIDIA. So in particular, x64 and ARM Linux. So something like Red Hat 9, Ubuntu 22, or Amazon Linux 23. And we also support Windows 11, or Windows Server 2022. And it is the same algorithm running in all cases. There's one limitation, however, and that is that the number of non-zeros that could be in the matrix is limited to 10 to 32, 10 to the power 32, so about 4 billion. And that's an NVIDIA limitation because they use a 32-bit integer to store the number of non-zeros there. And we hope that will change in a later release. So how to use it? As I said, it is available as part of Express 9.8 beta. It does not have a separate license in the beta release. And all GPU-dependent code is factored out into a new small library, XPRS CUDA. So whether you have a GPU in your machine or not, you can use the same Express version. And then if you just want to try the GPU version, we will check if you have appropriate drivers and hardware present, and then we just call the library functions as needed. It is deterministic on the same GPU, but not necessarily across different GPUs. And to run it, you just use the hybrid gradient algorithm, which is just activated with this barlog equals 4 option. And there's a new control we introduced, the PDHG GPU, which is off by default because you run by default on CPU. If you set that to 1, you will run on GPU if available. If not, then we will fall back to the CPU version. There's also a new precision control, PDHG precision, to select if you want to do single or double precision. As I mentioned in the talk, on CPU, we default to double precision, but on GPU, we default to single precision because there we have typically a factor 2 speed up versus the double precision version with very little impact on convergence. So we decided that the speed gain there was justifying changing the default. Also on the GPU, it has a reduced memory footprint. So if you run it, we will actually tell you that we are running GPU. We will tell you what card we found, how much memory it has, and what's the compute capability that it supports. This needs to be at least 7.5. And we will also print if you're using single or double precision, just to make sure that you're getting what you asked for. But the rest of the log is exactly the same that you would get from the CPU version. And if you have some large LPs or LPs that you are struggling to solve or take too much memory, we would be more than happy to take a look at them. You can just send them to expressperformance@fico.com, and then somebody will be in touch with you on how to get the large instance to us. So finally, I would like to talk a little bit about some downsides or some caveats or things that people should be aware of. We just took a test set of 189 instances, and we ran our barrier interior point solver, and it solved 170 of them. The hybrid gradient solved only 136, and these two solved verbs should actually be the different color because they are solved two different torts. So when they solved it, they didn't get the same level of solution. However, on larger problem, the hybrid gradient is generally faster than the barrier solver, assuming it can actually solve the problem. And so this is characterized by this trend line on the scatter plot. This is definitely below the 45-degree line. So for larger instances, you have a hybrid gradient faster than barrier if it can solve it. But because of the relaxed tolerances, the optimal solution can be very far off. And when we mean the optimal solution, I actually mean the optimal objective value. So there was a over 1% deviation on at least a third of the instances if you just run it to an absolute tolerance of 0.01. This is because the, let's say the dual errors are actually multiplied by the primal bounds to get the duality gap. So if you have larger dual errors and large primal bounds, then you can have a large deviation in objective value. The same is true for large primal violation and objective coefficients. So this is just a plot of the objective function relative error over all the instances that the hybrid gradient could solve. And for a good number of instances, it was nice, but as we say, larger than 1% deviation on a third of the instances. So that means, you have to know what you're expecting from the hybrid gradient algorithm and whether your application can deal with slightly less accurate solutions than what you would get from a simplex algorithm or a barrier algorithm. In some cases, it is justifiable to get less accurate solutions. In some other cases, this is a complete deal breaker. No, this is just something to be aware of and not just use it interchangeably in all applications. So that's the end of my talk. Thank you very much for attending again. If you have any questions or you would like to try Express, you can click on that QR code and that will take you to our licensing page and you can contact us there and somebody will be in touch with you.